Finished my book this morning. It was good. I want to watch the movie now. It's on Netflix. What is it? It's called The Woman in the Window. Okay, so that makes sense. So then in this direction is going to be the vector pointing in that direction is going to be the S partial. Did we learn that before? Like a different chapter? This feels like foreign to me. Okay, so did I need to solve for S here? I can just remember what and then just put that in like this. Oh yeah. So we find those. We cross them. Wait, this is thus n of 0. Why are we doing that? What's n? Oh, but the thing is, when you get this, you can't plug in one code here. You can plug in S2. And then when the function is not isolated, which is why you need S to 0 to so that's why. That'd be great. Wait, but is this right? Because I'm like looking this is 4, and then like you plug in A, B, and C. I know I did, but like, how was that to do it?
Okay. Okay, time to get started. I've been checking people's names off, by the way, as we go along. So I think I've got everybody who's here. Let me remind you of where we were last time. We were talking about flux, which is an old topic from chapter 3, of course. But we're talking about how to deal with flux when you have a curved surface and a non-constant vector field. Okay, so the big idea, flux is this expression. Why do we care about it? Well, it depends. Maybe you want to compute volume per unit of time of fluid going through a surface. Maybe you want to compute mass per unit time, whatever. It depends. And, tailor your vector field appropriately, right? But one way or the other, flux is the answer to that question, right? So So flux is something we're interested in. And here in a math class, I'm mostly going to focus on how to compute it and, mathematical properties, and the applications are, as usual, somebody else's problem. Right? So the formula that we have here, of course, this formula assumes that the vector field is constant. It assumes that your surface is flat. So how do we deal with if we have a non-constant vector field and a curved surface? Well, just with line integrals, and actually, let me flash back over here to the analogous problem for that led to line integrals. Curved path. Our old formula for work doesn't apply. So what do? We chop it up into little pieces, and on each little piece, it's approximately straight. The force is approximately constant. So we're going to do the same thing over here. We're going to chop it up into little pieces of surface, each of which is approximately flat, over which the vector field is approximately constant. Right? So it's morally the same idea, just surface instead of a curve. Okay. There's also the matter of orientation. Right now, this is an easier thing to talk about when you're talking about curves, because when you parameterize something, well, the parameterization, you're literally thinking of the parameters being time, and therefore of the parameterization as actually tracing out, actually moving along the curve. And well, of course, you would parameterize in such a way that that movement is in the direction that the curve is going, right? If the curve is oriented, sort of upward and to the right, you might say, in this case, well, then, yeah, parameterize it that way if you can, but the point is it's visually sort of more clear in the process. But we have an analogous situation here for surfaces. It's going to end up being algebraically, or I'll say intuitively, a little bit trickier. But again, flux means I need to know how much fluid is going through the surface. I need, therefore, to know which way it's going through the surface. And we define which way is the way that I'm talking about by way of unit normal vectors pointing through the surface. So again, this is all review from last time, but this is called the orientation unit normal. Just to specify that it's the orientation that is that helps define what our surface is that we're actually interested in the first place. Okay. All right. So with all of this set up, we look at each little piece, which we've already agreed on each little piece. It's approximately flat, right? And the vector field is approximately constant. And therefore, on each little piece, we get to recover our old formula here, F dot N times the area. And F dot N times the area, in this case, is that. So, this is all going to kind of come together here. And again, we're reviewing here, but chop it up, add it up. We have a whole surface. You chop it up into little pieces. You look at each piece separately. We just argued that on each piece, the amount of flux on that piece is F dot N ds. And with this, we have now a formula for flux. Okay, so I think this is about where we left off last time. Is everybody comfortable with all that? Okay, so yeah, we things went down algebraically a little bit differently when we were talking about line integrals, but nevertheless, we do have here a formula I'm going to call kind of analogous to this formula for line integrals. And I'll remind you this formula, where it comes from. This is just a kind of a rewrite of the one that we actually derived in the first place, F dot dx. Point being, this TDS over here, the T is, well, it's the direction that the curve is going. The DS represents how long the curve goes in that direction over the piece of curve that I'm talking about. And so TDS literally represents this vector dx. Right? So point being, this expression TDS it incorporates the direction and the magnitude of our dx vector. So the thing is, we're in fact, almost exactly the same situation over here. We just kind of, again, we come at it in a different way, and the physical application's different. So of course, the way we're going to put algebra on top of that's a little bit different. But check this out. We have in ds. What is in? In is a vector describing the orientation of that piece of surface. What is ds? Well, ds is the size of that piece of surface. So this product in ds is telling you what I'm going to call everything that you need to know about this piece of surface. It's telling you what the area is. It's telling you what the orientation is. And so this one thing in ds, because it's describing everything you want to know about that piece of surface, I think it's very reasonable. And this is standard notation to call that the ds vector, in the same sense that over here in the curves case, this dx vector is telling you everything that you could possibly want to know about that piece of curve. It's telling you what direction is that pointing. It's telling you how long it is, right? Same thing here. ds vector is telling you everything to know about the piece of surface. So that's the idea here. And that's why we call that the ds vector. Okay, pausing. Questions about that? Yeah.
So, but the ds vector is not n dot ds, is it?
No.
So
It's
what does it equal like algebraically?
Algebraically, the ds vector is the vector little n, the orientation unit normal vector at little n, scalar times this scalar called ds, d capital S,
Okay,
representing
so that's
size.
like the property of the dot product.
There's no dot product in here. No, this is just a scalar times a vector. It's a scalar vector product. Yeah. Is that cool? You remember scalar vector? You multiply vectors by numbers, right? That's all this is. Now, what you're going to do with that thing, is, you're going to dot it with this other thing. You're going to dot it with the vector field. Yeah, sure. But inside, in the process of making up the ds vector, it's just the scalar vector product of n and the ds scalar. Okay. All right. So you can use either one of these notations. I tell you what, in practice, most of the time as I'm kind of writing things down, I find this one really hard to beat. It's so compact and elegant, really. Again, it separates out the integrand vector from the what I'll call the domain vector, namely the vector describing pieces of the domain. So it's well separated, natural in that sense, and less pencil lead than this one. So I tend to gravitate toward this one. Right? But it's important to know that it is equal to this, because computationally or geometrically, sometimes it's nice to be able to see that unit normal vector in there. That's going to have its moments of really, really convenience. So you don't want to try to get by on only one of these. They're both useful, and make sure to realize they're the same. Okay. Good news, we know how to compute these things already, inadvertently. Accidentally, because now here's where we were, right? We talked about the chop it up, add it up, and each little piece of flux is this, and we talked about how you can rewrite in ds as the ds vector. So that's all just I'm putting it here just so we can have it as a reference. And okay, so how do I compute this thing? Well, here's our familiar ds scalar. It's the same ds scalar that we were looking at when we were doing scalar surface integrals. It's just representing a piece of area on our surface. We know how to write that in terms of a parameterization. In other words, we know how to pull that back through a parameterization because we already did so for scalar surface integrals. And before that, we did that for just plain old area computations. Right, so our old friend right there Everybody with me so far? Okay. Plug that in. And then something really nice happens, as it turns out. Now, y'all will notice, of course, this asterisk here. And so full disclosure, I am about to commit a math crime, and I'm doing it on purpose because there is enough going on here with, ignoring the subtle issue that I'm about to screw up on purpose. So let's focus on the computational aspect of this first, and then I'm going to come back and I'm going to tell you the little crime that I committed here. But if you want to be thinking about that, try to figure out what I'm about to do wrong. That's a good exercise. But anyway, here it comes. We made this substitution. I look now at this product. And notice I've got the unit normal vector. So that's a vector pointing in the direction of the normal. And then I'm multiplying it by the magnitude of my parameterized normal. And so, well, after all, then, this is a vector that's got the same magnitude as capital N, pointing in the same direction as capital N. This vector looks like a duck and quacks like a duck. And therefore it is a duck. Therefore it is the capital N vector. And again, crime, mea culpa. I will correct that error in a moment. But I'm only off by a little bit there. So anyway, let's go with this, and then we'll come back and consider later. So before I get ahead of myself, so that gives us yet a third form to think about vector surface integrals. So we've got these three. This is my favorite, again, because it's the more compact. This one has its merits because it's more sort of geometrically relatable, I guess you might say. You can see the normal vector, you can see the area. And then there's this point of view here. This one is the one that is the that uses the parameterization. This is the one that when you are going to take a deep breath and plow forward, plug and chug, and pull back through a parameterization, this is the one that you will use for that. So they are, though, keep in mind, all the same. Just different notations for the same thing. Okay, now let's compute one. So we want to compute a flux. We've been given the vector field, and we've been given the domain here. Let's see, it's okay, so we're looking at that paraboloid, and we're going to look at a particular portion of it over the unit square. Okay, so how do we compute this flux? Well, we know that in order to compute the flux from the parameterization, I'm going to be using this formula. We know that we're going to need our capital N vector. We know that the capital N vector comes from taking the partials, taking the cross product, right? So again, that's our old process that we've seen before. So, okay, so let's do that part. Graph parameterization, partials, cross product. Now, I just glossed over, several significant ideas from the course, but these are things we've talked about. So anyway, just make sure that you're good at that. Make sure you are super solid with how to do graph parameterizations. Again, it's something you need to be able. That again, my personal favorite parameterization method is that. Partial derivatives, of course, old news, but again, make sure you can do it. Cross products, again, kind of old news, but again, make sure that you can do it. Okay. And so now we're in business. We've got this vector field that was given, so that goes there. We've got our capital N vector that goes there, and you dot it on out, right? You dot. Now you also, of course, have to rewrite everything in terms of the parameterization. So don't forget that our parameterization means that we have formulas here for X, Y, and Z. Right, you got to be careful with that when you're plugging into a parameterization. So, for example, let's see here. Let me clean up my mess here. So this Z right here, Don't forget that Z is S squared plus T squared. So the Z squared is S squared plus T squared squared. Right? Does everybody see what happened there? When you're pulling back through a parameterization, the parameterization itself is what tells you how to plug in other words. Okay, so, and then, yeah, straight up dotted out, and now you've got a double integral, double iterated integral, and, plow forward. You all know how to do those. But again, make sure that you know how to do those. Questions? Yeah.
Why was the thing you did earlier not correct?
Oh, yeah. No, I haven't gotten to that yet. No, I'm deliberately sweeping that under the rug, and good for you for still thinking about that. We're going to come to that real soon. Yeah. But is everybody good with the computation process here? Okay. All righty. So, let's see here. Yeah, so let me go back real quick over to our business with vector line integrals. We did an example, not unlike the example we just did. And then we considered this question, right? So, does the value of what I'm computing depend on the parameterization? And the thing is, it's pretty tempting to say that it shouldn't. Well, of course it shouldn't. You're computing something physical. The parameterization is an arbitrary choice that you're making just to kind of get your hands on to compute what is and should be itself independently a well-defined thing, right? So how you parameterize shouldn't make any difference. And for scalar line integrals, it doesn't depend at all. Parameterize however you like. For vector line integrals, well, kind of subtleties. It mostly doesn't matter, but you do, of course, have to be careful. And in particular, you have to parameterize the correct direction. If you parameterize backwards, well, of course, you get the wrong answer by a factor of -1. In other words, if you compute the amount of work that it takes to go up the hill, but you were asked to compute the amount of work that it takes to go down the hill, well, it takes a negative amount of work to go down the hill. You recover energy going down the hill. So you're off by, it's just a minus sign, but it's also a huge swing in numbers, right? From a sort of, in an absolute sense. Okay, all right. So we're going to ask now sort of the analogous question for surface integrals. Yeah, oh yeah, question.
Say for on an exam, we realize that we parameterize it in the wrong direction.
Yeah.
Can we just put a -1?
I'm totally going to address that. Short answer, yes, but that's exactly where I'm going. Yep. So good thought. Okay, so flux. Does flux depend on how I parameterize? Well, I mean, again, mostly not. It's a absolute thing. It's a physical thing. The parameterization is an arbitrary choice that you make. You just have to make sure that you parameterize it the same way. And this is where things are sort of different than they are with line integrals. With line integrals, it's perfectly clear which way you're parameterizing. Just as the process of parameterizing defines what you comfortably visualize as a direction you're going along the curve. Mathematically, we have the exact same issue here. It's just not as sort of geometrically or physically relatable. So here's the story. If you have a surface given to you through which you want to compute a flux, keep in mind a reasonable question about compute the flux must come with an orientation. That orientation could go either of these two. I mean, it's perfectly reasonable to ask what's the flux in the upward direction. It's also perfectly reasonable and the negative, but perfectly reasonable to ask, I need to know the flux downward. Right? Baskets don't count in basketball if you shoot up through the hoop. Right? So let's consider, suppose our given surface, our given oriented surface, let's suppose it's oriented downward. Okay, well, if you then say, okay, well, I'm going to parameterize this surface. There's my parameterization. I'm going to use S and T as my domains, and I compute these various things, and I take their cross product, and I get my capital N vector like that. And then I talk about how, oh yeah, well, the capital N vector, now keep in mind, this capital N vector comes straight out of the parameterization. The capital N vector has never heard of your green surface that you were given and which way it was supposed to be oriented. Yeah. You write down that capital N vector, and then you start talking about how that capital N vector has, well, there's a unit vector pointing in the direction of that capital N vector. Well, the problem then is your orientation normal and your parameterized normal might be opposites, as they are in the case that I've drawn here. Right. So as this particular story played out, my orientation was downward. That was given. My parameterization just happens to be upward. Now, whose fault is this? Should I have seen this coming? Should I have realized as I was writing down that parameterization, oh, clearly this is an upward parameterization? No, not at all. You can't, it's not, it does not like a curve that you think of again as tracing it out. You can't really anticipate really which way you're going to parameterize. So this is, you know, you kind of, it's a grab bag, it's a coin flip. You get what you get when you parameterize. But it remains that these are not the same. And this is the issue. So that you asked me about, and that, you know, my little math crime, when I was doing this work here, and I said, okay, well, you know, it looks like a duck, quacks like a duck because it's pointing in the normal direction. It's got the magnitude of the normal. So boom, right? My math crime was that I assumed that the normal there, which of course comes from the given orientation, and the normal here wrapped up inside of my parameterization, this normal comes from the parameterization. And I just assumed that these were the same. I assumed that the green normal is the same as the purple normal. And of course it is not necessarily. Right. So the upshot is coin flip. You might parameterize the wrong way, therefore be off by a factor of -1. And to your question, yeah, don't sweat it. If you have identified that you accidentally parameterized it backwards, just say, whoops, haha, parameterize it backwards. Here's my minus sign, and then continue on. And it's fine. And yes.
How do you know you parameterize?
Yeah. I'm going to show you an example. Yeah. So here we go. Now, this example that I've got here, this question here is identical to the one that we did a couple minutes ago, with the one change being that here I'm indicating that this surface is now to be understood as oriented downward. I shouldn't use that in purple. I should do that in green. So my given surface, this surface is by definition now downward. So what do? Do I consciously try to parameterize downward? Oh my gosh, no, I don't even know how to do that. What you do is you try to parameterize any which way you can. I look at this as a graph and I think, okay, graph parameterization. Let's use our favorite parameterization. And we take the partials and we take the cross product. And here's where you pause. Here's where you stop and take stock. Right, draw, and it's so tempting, by the way. You got to resist the urge when you get to this point. You're like, oh my God, I see my capital N, I see daylight. I'm just going to plug that in here and crank. Right, you got to resist that urge because we do not yet know if our parameterization is appropriate. So what you do is you got to compare. Now, the language of how orientations are described, it's different for every surface, and I'm going to talk more about how to describe orientations with language in a couple of minutes here. But in this case, you see the surface was given as oriented downward. I'm going to say that downward means, okay, the z component needs to not be positive. Right? It doesn't mean that it's oriented straight down. Well, of course not. It's got to be perpendicular to the surface, but at least it's, you know, somewhat downward. And you can see from this parameterization, my normal vector is not, right? My normal vector is clearly pointed somewhat upward. That is incompatible with the given downward. And so this is how I realized, somebody asked over here, that parameterized it backwards. And so again, don't worry, you don't have to start all over. You just say, no, this was not consistent. So I account for it with a -1. Here's my -1. This is the recognition that I parameterize backwards, realize that I parameterize backwards, and therefore that I can just keep on trucking and everything will work out fine. Yep.
Out of curiosity, what does it mean to parameterize backwards? Would like the S and T be changed?
It just means that when you wrote down that parameterization, again, it's visually, geometrically, it's hard to see it coming, but this parameterization actually encodes a normal direction, and this one happens to encode that way. So I literally parameterized this surface that I have drawn here. I parameterized it upward. I just can't. If you try to see that in the formula, you're going to fail. You can't. Yeah, and that's what I'm saying. This is very different from curves, because when you write down a curve, right, you parameterize a curve, you can see. I mean, by virtue of what as your parameter moves, you can see your point moving along the curve. So it's just not as visible here at this stage, but it is, of course, perfectly visible in the punchline. You see what I'm going with that? Yeah. So there is something about this that's intrinsically less satisfying because we can't see it coming. And that makes it confusing. But again, it remains, just look and see. And if you're backwards, put in a minus sign and everything's fine. Now, I emphasize, let's see here, let me clean up the mess here. We've fixed our error here with this -1. There it is, -1. Orientation issue resolved. Some students will then make the mistake of thinking, oh, but that also means that this is backwards. And so they'll, rather than recopy the capital N vector, they'll just arbitrarily put minus signs in all the coordinates of the N vector. Now you've accounted for the minus sign twice, which of course is the same as not accounting for it at all. 2 minus signs is not the same as 1 minus sign, right? So it's very important, I think, to do it the way I've got it described here. Recognize your minus sign externally, right? This communicates the important thought that you realize there's a contrast between the given and the parameterized orientations. If you stick an arbitrary minus sign into here and make these plus and that minus, then now this and this are incompatible. Now your capital N vector doesn't make any sense. That capital N vector is defined as something that comes out of the parameterization. It needs to remain something that comes directly out of the parameterization. So don't, but where you put the minus sign matters in terms of clarity of your work, right? So make sure to make some minus sign external, and then proceed with the misoriented capital N. You've already corrected its error. Okay, so let's talk about language a little bit. How do we talk about orientations? Let's see here, let me zoom in. Here we go. Every surface is different, have different sort of complications to deal with. So if you take, for example, this surface here, well, one orientation would be like this. I better do this with a pencil. One orientation would be sort of like this. And how would I describe that green orientation? All the vectors are pointing in different directions, sure, right? I can't verbally describe exactly the directions they are all pointing. The thing is, they all have something in common, and furthermore, something that distinguishes them from this other orientation that I need to contrast it with. Right? So we have to think about, what is it that the green vectors all have in common, and furthermore, none of the blue vectors have. And that is that, at least to some extent, those green vectors are all pointing, well, at least somewhat upward, and none of the blue vectors are pointing in any sense upward. So if I say upward, yeah, it's not perfect. I'm not saying the orientation is exactly straight up. Of course not. That's implausible. But that word upward, it removes any possible ambiguity. If I say upward, clearly I'm talking about that green orientation there. Does that make sense to everybody? Okay. Now, that said, there are other ways that you could make this distinction. I think it's kind of plausible to say that all those green vectors are pointing inward, kind of, a little bit. I mean, it's not that there's a well-defined inside in this case, but I think this would communicate the thought. So I give this a partial check as a reasonable terminology. Now, by contrast, if you look at a sphere, your surface being this sphere here, or any other closed surface, and you want to distinguish, let's say, this orientation there. So this terminology here, upward versus downward, doesn't make any sense. Some of those vectors point upward, some of them point downward. The one I'm trying to distinguish it from, some of them point upward, some of them point downward. So I'm going to say that this is this is an unacceptable choice of language. That does not help me at all. If you say I look at the unit sphere oriented upward, I don't know what that means. Everybody see? But inward versus outward makes loads of sense. The blue vectors, all of them pointing inward, and none of the green vectors pointing inward. And then likewise for outward. Yes?
So when for upward, downward in the previous problem, what would you look at for inward, outward?
Yeah, that's right. It's something a little bit different. That's in this case, because it's a perfect sphere, you could just what you'd want to do is compare the position vector with the orientation vector. And if the position vector and the orientation vector are pointing the same direction, well, then that's outward. And if the position and the orientation are pointing opposite directions, then that would be inward. So yeah, algebraically, it's going to be different every time. And I can't enumerate all possible cases and give you, the mechanical, rule for distinguishing, but you have to, look for the cues as they might possibly be available. Yeah. Is that, I mean, I know that's not perfectly satisfying, but that's what it is. Yeah. Yeah. Okay. And then thinking about this paraboloid here, a reasonable thing, I think, would be to say, oriented in either the positive y direction, as all of these inward pointing vectors are clearly going, versus the negative y direction, which of course the other one. Okay, but definitely not upward versus downward. That makes no sense at all. Doesn't distinguish anything. Inward versus outward, again, kind of, I guess in a pinch, I guess that's sort of okay, but suboptimal and not really as useful either. Okay, so moving along. Sometimes you get lucky. You want to make sure to resist the urge to every time you find yourself looking at a flux integral to compute, to always parameterize and plug and chug. Sometimes there's good news out there, and stuff just works out and life is good. So here's an example. I've got a sphere here. This is sphere of radius 3. You see it's oriented outward, and I've got a vector field given, and I want to compute a flux. So now, again, you could parameterize. Let's try to think how that's going to play out. If I parameterize, I'm probably going to use a spherical graph parameterization. That means there's going to be a lot of trig. That means that when I find my capital N vector, I'm going to be taking cross products of partials of lots of trig. And, you know, I mean, it's not that it can't be done, but it's you know, it's a little tedious, and all else being equal, nice to be avoided. So the alternative here is to just notice that because of the geometry, I can actually immediately write down my orientation unit normal. It says right here, oriented outward. This being a sphere, gotta love spheres. Spheres have so much, you know, geometric symmetry, and they're just so regular. It's really nice. Being a sphere, that normal vector, that outward normal vector, is exactly in the direction of the position vector. In fact, it's the position vector divided by 3. Because spheres are awesome. Well, sphere centered at the origin. Everybody with me there? Now, I didn't have to do any trig. I didn't have to do any cross products or partials or nothing. Right? Just, you know, geometric observation. And I've got now I don't have, you know, I'm not saying that this is, you never need to do a parameterization, because how do I compute integrals like this? Well, I parameterize, right? But what this does is it gives us an opportunity to maybe hope for good luck. And here's where you get lucky, and because I have the formula for the unit normal, and this dot product turns out to be 0. And therefore the integral is 0. And we wouldn't have had a hope of using that much, you know, recognizing that much convenience without, you know, pausing, taking stock, looking for the clever opportunity to write down that unit normal vector. So heads up. Again, life is full of lucky coincidences. Correction, physics and engineering are full of lucky coincidences, chock full, right? And so capitalize on those when you can. You just can't afford not to capitalize on these kinds of things. Yeah.
So in order to find this coincidence, we would have had to decide not to parameterize first. So
Yep.
should we just do this every time in terms of X, Y, and Z?
The hairs on the back of my head start to stand up when I see spheres centered at the origin. I'm like, uh-oh, sweet. That's an easy one. Right? I know that my normal vector is going to be something nice there. And so in that case, yes. Now, if you are given something like you know, this surface here, we're looking at part of a paraboloid. I don't really, how am I? I guess I could play clever games with gradient vectors and come up with a normal, but it doesn't seem particularly easy. And so here I wouldn't think particularly to do that. Does that make sense? So you always want to try to always think in terms of what's the path of least resistance. In this case, not so much. And in this case, you know, again, this is an easy lucky break to look for. Yeah. All right. Here's another different kind of lucky break that happens sometimes. So here, my surface, a little bit of a weird surface. The surface sits inside of this plane, y equals 3. Specifically, it's the part that is inside of a certain curve. And you notice those are 4th powers. So this is not a circle, right? But this is, you know, vaguely round-ish, I guess I'll say. So there's our surface. You'll notice, furthermore, it's oriented in the positive y direction. And so, well, I can instantly write down then my normal vector. And, excuse me, my orientation unit normal vector. So right off the bat, I know that. And that instantly makes me not care about certain aspects of the vector field. You notice the vector field has 3 coordinates here. I instantly don't care what these 2 coordinates are. Don't care what that is, because that's about to get multiplied by 0. So Sweet. Now, will this carry through? Can I compute the rest of it? Well, I don't know, remains to be seen. But that one observation that saves you, in some sense, you made 2/3 of the work go away with that one nice observation. So that's cool. The other clever observation to make is that my surface, where I'm doing this integral, this surface here, because it sits inside of y = 3, that means that everywhere on that surface, I know y is equal to 3. And if y is equal to 3, then I know that this second coordinate is also 0. And boom, everything just crumbled and blew away in the wind, and we're left with 0. So clever observations. Right now, if you plow forward algebraically, it's not that you can't do it, but when you can capitalize on good news, by all means, do it. Everybody on board? So there's in some sense kind of 3 clever observations that we could make here. 2 in this one and 1 in that one, and I don't rule out the possibility there's other bits of cleverness that you can capitalize on. So always head on a swivel, right? Always be thinking about, hey, is there anything particularly convenient about the problem that I wonder if there's some way I can capitalize on that. Yeah.
Can you please explain one more time why it's a convenience, or how we're able to find n so easily for the sphere but not for the parabola?
Oh, yeah, because spheres are highly symmetric. Spheres are like the most symmetric surfaces ever, right? In their ways. And spheres, it just happens to be, let's say it this way. If this were the Earth, if this were the surface of the Earth, up is always a multiple of from the center of the Earth. Let's say it this way. The center of the Earth is always straight down. Right, so it's just spheres this is a unique property of spheres, right? So this is all in thanks go to the fact that this is a sphere. And in the case of the paraboloid, well, paraboloids are kind of symmetric. Where did this go? Oh yeah, here it is. Kind of symmetric, a little bit, sort of, but not the same way. And I can't. It's just there is no that immediate of a clever bit that I can take advantage of here. Yeah. Okay. So let's see here. A little bit of terminology and notation I need to throw at you. Let me go back to the line integrals business here for a second, and let me remind you. Where is it? Yeah, by the way, there was fortunate geometry in the line integrals case, right? So in every context. But so remember, with line integrals, there was this sort of funny business where if you look carefully at your domain differential. This is your position differential, of course. You just kind of notice that, well, yeah, that I can expand it out in coordinates, and having expanded out in coordinates, I can rewrite it, and then the individual coordinates start to make sense. And so, for example, I can rewrite the dx vector as well, dx, dy, dz. This is then coordinate differentials that you can ascribe to the position differential. So, well, good news, morally identical thing happens with surface integrals. So we have a formula for our normal vector. I can write that out in coordinates. I can compute that out. And I did this several pages back. That would be last time, where I observed that this was going to be useful at some point, and here we are. But this is a formula we've seen before for a capital N vector. And then you notice that, okay, well, I can coordinate-wise multiply that out. And, what do you think we should call this thing here? I mean, thinking back to the change of variables section, right? This determinant right there, that's what you multiply by ds dt to get dy dz. So doesn't it make sense to call this product dy dz? Seems reasonable. And likewise for the rest of them. So this is dz dx, and this is dx dy. Now, this is just a notational choice. There are some awkwardnesses about this notation. Remember, we talked about this, that this factor right there, being as it is a determinant, is order dependent. The Z and the X, you can't just kind of trade those around. The Z has to come first. Otherwise, you're trading columns. You're introducing minus signs. No fair. Can't do that. Right. So likewise, then it follows this is not the product of two scalars that it kind of notationally looks like. This is notational shorthand for something that is very order dependent, and therefore this is order dependent. You cannot write dx/dz here. That is wrong. It's not notationally uncomfortable. It is wrong. Right, so heads up and be careful about that. Anyway, it remains, though, that we've got this coordinate formula now for our surface differential ds. And so you can plug that into the formula for a line integral, for a surface integral. So our surface integral formula was this. We just got through writing down the ds vector in coordinates like that. Of course, our vector field has coordinates too, or has components too. And you can just dot that out. I mean, straight up crank out that dot product, and this dot product becomes, well, all of this here. So this is what I call a coordinate surface integral. And really it's just notation. I'll call this coordinate surface integral notation. The big point to realize about it, of course, is just a notational alternative to the exact same flux integral that we've been talking about. This is not really a new kind of integral. It's just a different notation. You know, longer and less intuitive. Right? So the appeal of this notation here is not clear. In Math 219, it's fairly rare that this is actually useful, or at best, its uses are that it, in some cases, might be a little bit more compact. Certainly not here, but you know, maybe depending on the circumstance. But just like with coordinate line integrals, just for the record, yeah, it is actually from the point of view of work that's done at a much higher level than Math 219, this is actually quite natural. This is an example of something called a differential form. Differential forms are powerful, sophisticated, really pretty awesome stuff, but it's just not what we're going to be doing in this course. So the main reason y'all need to be aware of this is that this notation, just like coordinate line integrals, is in common use. Right, so you are going to see outside of Math 219, you're going to see people write this down, and they're going to expect you to know what this means. And so what I suggest when you see this, just think to yourself, oh, okay, all right, it's that coordinate surface integral. Okay, what they mean is this. And then just infer from what's written here, you can infer that these separate scalar integrands here are just, okay, that's what allows you to understand what the vector field is that you're actually doing a surface integral of. You're actually taking flux of. Is that cool? All right. So with the remaining 30 seconds, I think I'll just go ahead and repay what I'm sure I owe you. We'll draw the line right there, and see y'all on Friday. Have a good day. As usual, if you came in after I did attendance, make sure I mark you down. All right, see y'all later. Let's see here. Stop.